everyone, welcome to my YouTube channel Net Physics by Tanya. In today's lecture of nuclear physics, we will study what is parity of a wave function. A parity transformation is the flip in the sign of one spatial coordinate. In 3D, it can also refer to the simultaneous flip in the sign of three spatial coordinates. Here, if you invert the coordinate system with respect to origin so that xyz coordinates are replaced with -x, -y and -z, you can see in both the diagrams that it is the x-axis, its y-axis and its z-axis, and after having the parity operation, or we can say space reflection, the axes are being inverted and now it's from origin it's -x, -y and -z, and you can see that in this figure the y-axis is in this direction. Now after parity operation the y-axis is being inverted. Similarly for z-axis you can see it is being inverted, and also similarly for x-axis it is being inverted. Now the new physical quantity will be dependent on -x, -y and -z. So what happens to the wave function under such parity operation or space reflection? Now if you look at a Schrödinger wave equation, that is minus h cut square upon 2m d square psi over dx square plus vx psi x is equals to e psi x. That is the equation 1. So that's a Schrödinger equation for a quantum system which has a potential field of some function this vx, and solution of this Schrödinger equation is psi x here. Now under parity operation we have to simply substitute x to -x in this first equation. So after substituting from x to -x we will get the equation minus h cut square over 2m d square psi minus x over dx square plus v of minus x psi of minus x is equals to e psi of minus x. That is our equation number 2. And the equation number 2 is after parity operation. So you can see here that this first equation and second equation both are different. So we will use the property of potential that in any of the potential v of minus x is equals to v of x. So we will use this value in the above equation, and the new equation will become minus h cut square over 2m d square minus psi of minus x over dx square plus v of x instead of v of minus x, using the property here psi of minus x is equals to e psi of minus x. Now you can see, now equation number 1 and 3 you can see here are similar except the solution psi of x and psi of minus x here. And you people might be thinking that why I have replaced or substitute only this x and not any other variable, because this equation is only for 1D, so there is only one variable x, that's why I have substituted x only here. So as in the previous slide you have seen that equation 1 and 3 are similar except the solution psi of minus x and psi of x there. So you will realize that solution of Schrödinger equation is basically result of nature of potential, and nature of potential is same in both equation number 1 and 3, that is v of x and v of minus x. So the solution of equation number 1 and 3, that is psi of x and psi of minus x, should have the same form. So if the potential is symmetric with respect to reflection, then for those cases physically observant quantities should remain invariant. So if the physical quantities are invariant, then the conclusion is that the probability distribution should also be invariant. So psi of minus x mod square is equals to psi of x mod square. So this opens the possibility of two different cases if you remove these square terms on both sides. So the possibility is like that after removing the square terms, psi of minus x will give plus minus of psi of x. So case 1 will have psi of minus x is equals to positive value of psi of x, that is known as even parity wave function. And in case number 2, psi of minus x having negative of psi of x, that is odd parity wave function. So we can show this by taking a simple example of a particle in an infinite square well potential. So you can see here that n equals to 1, that is ground state, that is first excited state, then second excited state, and this is third excited state, and up to so on. So if you consider this potential well, that is the center x equals to 0 here, and the value varies from minus a by 2 to plus a by 2 here. Now, if you look at the nature of infinite square well, and if it is centered at origin x equals to 0 here, you will see that it is symmetric with respect to direction of its axis. And here the potential well goes from minus a by 2 to plus a by 2 according to this width. So you will see here, if I consider the one point here, that is psi of minus x, and the another point here for the ground state wave function psi of x, then it will show symmetric behavior as like as in the potential v of minus of x equals to v of x. So it is showing the same behavior. It will show for the ground state symmetric behavior. Now for the first excited state wave function, if you will consider one point here on this peak and the another point here downwards, so you will see that psi of minus of x is giving minus psi of x and showing anti-symmetric behavior. Now similarly for the second excited state, if you will consider one point here and the another point here, you will find that psi of minus x will gives equals to value psi of x and shows symmetric behavior. So alternatively, for the next excited state, that is our third excited wave function, it will again give us the value, like if you consider one point here, that is psi of minus of x, and the another point here, that is psi of x. So it will give you the value that psi of minus x equals to minus psi of x. So this will show you the anti-symmetric behavior. So you can see here that there's a pattern of showing the alternative symmetric and anti-symmetric behavior, or you can say that even parity or odd parity alternatively. So either the wave function is symmetric with respect to the reflection or the wave function is anti-symmetric with respect to reflection. The wave solutions of such a potential consist of alternatively even and odd parity wave function, like symmetric, anti-symmetric, symmetric, anti-symmetric, or you can say even odd, even odd. Now other examples include the harmonic oscillator, in which the potential is symmetric with respect to the reflection along the origin of x-axis, and you will find the ground state wave function is even, first ground state wave function is even, first excited state is odd, and up to so on. So here it is the diagram of harmonic oscillator, and similarly in hydrogen atom and in atomic nucleus, you will find the same behavior as the even odd parity or the alternating behavior like symmetric and non-symmetric. So in nucleus, there is one particular way of treating the nucleus in the shell model, where the nucleus is assumed to behave having a potential in which the nucleons are existing inside the nucleus. So this potential is also symmetric to the parity operations, and so therefore nucleons, here you can see the neutrons, protons will also show alternatively even and odd parity wave function. So most physically observable quantities are invariant under parity transformation, as you have seen in the previous slides, and because the probability distribution is also invariant. Therefore, different kind of interactions happen between particles under parity transformation, and they do not distinguish between left hand and right handed systems. This is true for different kinds of forces like nuclear forces and electromagnetic forces and in classical mechanics, except some exceptional cases. When it comes to weak interactions, the parity conservation is violated, and there are certain situations in which nuclei undergo beta decay process. Then there is certain presence in certain direction in which electrons are emitted, and these electrons are not conserved under parity operation. So you can remember that sometimes the parity conservation is also violated in some exceptional cases. Thanks for watching. Stay tuned for some more videos. Like, share and subscribe my channel. Thank you.